Welcome to Formula 1 Maths. This is Mixed Exercise 12.01. GCE A-Level Pure Maths Year 1. Mixed Exercise 12.01 is on differentiation. We've got two questions to answer. Question 1. A curve has the equation y is equals to f of x. Given that f of x is cubic with the coefficient of x squared equal to the coefficient of x. The curve with equation y equals to f of x passes through the point 0, 5. The curve with equation f of x has stationary point at 2, minus 3. A. Find f of x. B. Show that the stationary point at 2, minus 3 is a minimum. So we start by writing down the general equation for a cubic curve as follows. Y is equals to f of x is equals to ax cubed plus bx squared plus bx plus c. We have b here and b here because the first condition states that the coefficient of x squared is equal to the coefficient of x. The second condition states that y equals to f of x passes through the point 0, 5. That means when x is equal to 0, y equals to 5. So we can do our substitution in this equation here to get the following. F of 0 is equal to 0 plus 0 plus 0 plus c equals to 5. And then we solve for c to get c equals to 5. So this constant c is equal to 5. The third condition states that f of x has stationary point 2, minus 3. That means when x equals to 2, y is equals to minus 3. So again, we can substitute these values into the general equation here. We are going to get f of 2 is equals to a times 2 cubed plus b times 2 squared plus b times 2 plus 5 is equals to minus 3. Simplify this and you're going to get f of 2 is equals to 8a plus 4b plus 2b plus 5 equals minus 3. A further simplification gives 8a plus 6b equals to minus 8. Then we can divide all the terms by 2 to simplify it further to get 4a plus 3b is equals to minus 4. We can now label this equation as equation 1. The third condition states that the curve with equation f of x has stationary point at 2, minus 3. That means I need to differentiate this equation here with respect to x. And if I do that, I'm going to get the following. Y is equals to ax cubed plus bx squared plus bx plus c. If I differentiate that, I'll get dy dx is equals to 3a squared plus 2b x plus b. So I get the following. Please note that dy dx can also be written as this. But because this point here, 2 minus 3, is the stationary point, it means that if I substitute 2 into this gradient function or derivative, I'll get 0. So at the stationary point, dy dx equals to 0. And that means f of 2 is equals to 0. And so I'll do my substitution and I'll get 3a times 2 squared plus 2b times 2 plus b is equals to 0. Simplify. Get 12a plus 4b plus b equals to 0. Further simplification gives 12a plus 5b is equals to 0. We can now label this equation as equation 2. We've got equation 1, equation 2, two linear equations with two unknowns. So we solve the two equations simultaneously by multiplying equation 1 by 3 to obtain the following. 12a plus 9b is equal to minus 12. I'll then subtract equation 2 from this equation here. So if I do that, I get the following. 9b minus 5b will give 4b, and minus 12 minus 0 gives minus 12. So we get 4b is equal to minus 12. Solve for b, and you're going to get minus 3. Having got b, we can substitute this value into equation 1 to get the value of a. And so, if we do that, we are going to get 4a plus 3 times minus 3 equals to minus 4. Simplify and rearrange to get 4a is equals to minus 4 plus 9. And a is equals to 5 over 4. So we've got all the values now. We've got a, we've got b, and we've got c. So all we do now is to rewrite this equation with the values we found. And we are going to get y equals to f of x equals 1.25 x cubed minus 3x squared minus 3x plus 5. And that is the function required for a. For b, we will need to differentiate this equation here we found. And we can make it simpler by writing the 1.25 as 5 over 4. That if we differentiate that, we are going to get dy dx equals to 15 over 4 x squared minus 6x minus 3. And so we get this. To show that this point is a minimum, we have to find the second derivative. So we differentiate dy dx to get the second derivative. And if we do that, we are going to get d squared y dx squared is equals to 15 over 2 x minus 6. And so we get this. To find out whether it's a minimum or a maximum or a point of inflection, we will substitute the value of x, which in this case is 2, into this equation. So when x is 2, d squared y dx squared is equals to 15 over 2 times 2 minus 6. And this gives 9. So that means the second derivative, which is given by this, is bigger than 0. That means it's positive. And because it's positive, we can conclude that this point is a minimum. Question 2. A solid right circular cylinder has radius r centimeters and height 8 centimeters. The total surface area of the cylinder is 500 centimeters squared. A. Show that the volume V centimeters cubed of the cylinder is given by V is equal to 250R minus pi r cubed. B. Given that R varies, use calculus to find the maximum value of V to the nearest centimeters cubed. C. Justify that the value of V in B is maximum. So let's draw a right circular cylinder and we get something like that. The radius we know is R and the height is H. Now we are told that the total surface area of the cylinder is 500 centimeters squared. We have the top area given by pi r squared, the bottom pi r squared, and then we have to find the curved surface area. But the curved surface area of a cylinder is given by S is equal to 2 pi r times h, or the circumference times the height, where r is the radius of the cylinder and h is the height of the cylinder. So the area of the top is pi r squared, and the area of the bottom is also pi r squared. That will give 2 pi r squared. We can then add the area of the curved surface, and we're going to get 2 pi r squared plus 2 pi r h. So the total surface area is given by this expression here. But we are told that this is equal to 500. So let's equate that to 500. We can divide every term by 2 to simplify it to get pi r squared plus pi r h equals to 250. We can now rearrange and make h the subject as follows. So h is equal to 250 minus pi r squared over pi r. We also know that the volume of a cylinder is given by V is equal to pi r squared times h. So the cross-sectional area is pi r squared times the height, which is h. And so V is equal to pi r squared h. We can now substitute this value for h over here to obtain V equals to pi r squared times the height, which we got over here. At this point, we can reduce the fraction by cancelling the pi and the pi over there. And one of the r's here will cancel one of the r's here. And that means we are left with V is equal to r brackets 250 minus pi r squared. Expand the brackets to get 250 r minus pi r cubed. And this is the expression required. And so that's A. For B, we need to differentiate V with respect to r. So we are going to get dV dr is equal to 250 minus 3 pi r squared. But for the maximum value of V, dV dr must be equal to 0. So we can now equate this to 0 to get a value of r that makes V the maximum. And so 250 minus 3 pi r squared is equal to 0. Rearrange to get r squared is equal to 250 over 3 pi. We want r, so we're going to find the square root, and we're going to get the square root of 250 over 3 pi. Evaluate this, and you're going to get 5.15 centimeters. So the radius is 5.15 centimeters. We can use this value here to get the height by substituting 5.15 into this equation here to get h. So let's do that. We get the following, and evaluating gives 10.3. So the height is 10.3. But we know that the volume is given by pi r squared h. So for the maximum volume given by V max, we get pi times r squared, because r squared is given by 250 over 3 pi. So instead of doing 5.15 all squared, we simply replace the r squared with this value here, which is more accurate. And then we multiply by 10.3, which is the h that we got over here. So we can cancel out the pi, and V max now becomes 350 over 3 times 10.3. And this, when evaluated, gives 858 centimeters cubed. And this is the maximum volume of the cylinder to the nearest centimeter squared. For C, we need to justify that the value that we got in B, which is 858 centimeters cubed, is a maximum. We will need to find a second derivative with respect to r. So we're going to differentiate this expression here. And so when we differentiate, we are going to get minus 6 pi r. And we can substitute the value of r, which makes the volume a maximum, and that was 5.15. So let's do our substitution. And this, as we can see, will give a negative value. And so we can say that the squared V, the r squared, is negative, and therefore V is maximum. And this is the end of this session of mixed exercise 12.01. Thank you for watching. I'll see you in the next video.